Welcome to Mitchell Maths. In this video we're going to have a look at some questions involving distance time graphs. With distance time graphs we have distance or displacement plotted on the y-axis and time across the x-axis. Now the difference between displacement and distance is displacement is a vector, so you can basically direction matters, whereas distance is just a magnitude where it's just size. And there's going to be a few different types of questions which you would get, which we're going to look at. The first of which is where you're given some information and you need to plot the graph. So if we have a look at the information they've given us, they've said the train's going to leave at 9 AM and it's going to travel at an average velocity of 240 miles per hour and arrives at the second station for 10:30. So what I need to do is I need to find how far has that train travelled from 9 AM till 10:30 AM. Well, 9 AM to 10:30 AM is 1.5 hours. And if I think about my speed, distance, time equation, I've got speed, distance, time. In order to calculate the distance travelled, I need to do speed multiplied by time. So I'm going to do 1.5 hours multiplied by 140 miles per hour. And I need to use hours because the units given to me are in miles per hour. If it had been in seconds or minutes, then I would have needed to convert one of these units. Now 1.5 times 140 is 210. So I know that at 10:30 the train will have travelled 210 miles basically. So if I have a look at the scale, well, 250 take away 200 is so it's 50 and it's represented by 10 boxes. So if I think about each box, that's going to be 50 divided by 10. Each box is going to be equivalent to 5 miles. If it's 210, that's going to be 200 plus 10. So I'm going to need to go 2 boxes up. So I'm going to plot here. And what I do is I draw a straight line from 9 AM right up till 210 at 10:30 AM. The next bit of information it tells us is a train waits at 30 minutes before departing. Okay, well, in that 30 minutes, it's not going to travel anywhere. So at the end of that 30 minutes, it's still going to be 210. And I just draw a straight line connecting those two dots. And then it tells us that the train travels at an average velocity of 80 for 30 minutes before arriving at the third station. Now I'm going to do speed times time again, but this is in minutes. So I'm going to need to convert minutes into hours. And you do that by dividing by 60. So 30 minutes is equal, and you probably should know this anyway, it's equal to half an hour, isn't it? So 30 divided by 60 is a half. Therefore I'm going to do 80 multiplied by a half, which is 40. So after 30 minutes at 11:30, it will have travelled another 40 miles, which, well, 210 plus 40 is 250. So I'm going to plot up here. And then it tells us that the train waits at a third station for 30 minutes, so that's going to be like this again. And then it travels back in the opposite direction to the first station at an average speed of 125 miles per hour. And it just says speed here because it's going at the opposite direction, so it'll be a negative velocity. So it's going back to the first stage. Now because this is displacement, this is how far it was from its starting point. So if it's going backwards, it's actually going to be returning to its original position. And we need to find out how long it's going to take to get back if it's travelling at a speed of 125 miles per hour. And we can see from this equation we do distance, which is 250, divided by speed, which is 125, and that means it'll take 2 hours. So if we start at 12, it means it'll get back at 2. So we just draw a straight line from here down to here. And if you draw this neatly, it should look something like this. So you have the train travelling to the first station, 210 miles, waiting for 30 minutes. Then it travels the remainder of the station to the third station, waits for 30 minutes, and then it travels back at 125 miles per hour without making any stops. So you have no pauses on the way back. Right, now we're going to have a look at a different question. So that was drawing a distance time graph. You might also have to interpret distance time graphs. So Peter went out on a social bike ride. He cycled to a local cafe where he stopped for a drink. He then cycled further, arriving at his final destination for 1 o'clock. How long did Peter spend at the cafe? Well, we know how long he spent. Well, if we look at the graph, this is when he set off. This will be when he was at the cafe, and this will be his final ride, and then he'll have reached his destination. So if we look at the time spent at the cafe, well, it was from 11 till 12, so it was exactly 1 hour. How far did Peter have to cycle to reach his final destination? Well, we're going to need to use a scale here, so it's 50 take away 40 each. So those 10 boxes are equal to 10 miles. Because if we do 50 take away 40, it's 10. And because it's 10 boxes and 10 miles, we know that each box is the equivalent of 1 mile. So we can see it's 40 plus 2 boxes, so that will be 42 miles. So that's how far his final destination is. And part C, what was Peter's average speed during the first 2 hours of the journey? So in the first 2 hours, that's from 9 to 11, we can see it's a straight line. Now, when you're using distance time graphs, the way you can calculate speed, if we think about the equation anyway, it's speed, distance, time, but because speed is distance divided by time, it's actually the gradient of the slope gives us how fast the person is going. So we need to measure the change in y over the change in x, or the distance over time. Well, the distance travelled in the first 2 hours was 30 miles, and the time taken was 2 hours. So 30 divided by 2 is 15. So his average speed was 15 miles per hour, because I've done miles divided by hours. So it's very important to get put those units on. Right, and this question, what we're going to do is we're going to compare the distance time graph of 2 cars which have set off in a race. And we've got car A and car B, and it's a drag race, which is just a straight line where 2 cars see which one can go the fastest. And we're being asked which car won the race. Well, the one that won the race will be the one that finished in the shortest amount of time. And we can see that car A finished at around 8.4 seconds, whereas car B finished around 8.8 seconds. So it will be car A. Which car had the greatest initial acceleration? So initial acceleration means the acceleration off the line. If we look at car B on the graph, we can see initially car B pulled into the lead, which means off the line, the initial acceleration of car B was greater than the initial acceleration of car A. So we're going to have, that'll be car B. Part C, after approximately how many seconds did the 2 cars pass each other? So this is where that it intersects. So if we look at the point of intersection, it's around this point. There'll probably be a bit of leeway here. So if we read down to this point here, well, we know that halfway between 6 and 8 is 7. And we can see that there's 1, 2, 3, 4, 5 boxes. So we're dividing 1 second into 5 parts. So 1/5, which 1 divided by 5 is 0.2. So each box, if we divide 1 second into 5 parts, each box is equal to 0.2 seconds. So it's 7, and it's 1 box, so it's 7.2 seconds. And there'll probably be a little bit of leeway because it's not quite clear. It could be also, you could probably also say 7.1, possibly. So 7.2 seconds. So sometimes when it's not clear, they will give a bit of leeway with answers. What was the difference in time taken for the 2 cars to complete the race? Well, we can see this one finished here. And we see car A, if we read down, it finished here. And we said that each box is equal to 0.2 seconds. So that would be 9. Well, 9 take away 0.2 would be 8.8. So car B took 8.8 seconds to finish the race. And car A was, well, it's 2 boxes from 8, so it's 8.2, 8.4. So it took 8.4 seconds. So the difference between the time taken by the 2 cars is 0.4 seconds. So that's a question where you compare two different cars or the travel graph of 2 different objects on the same graph. Right, for the final one, the distance time graph shows the distance travelled by a particle over 2.5 seconds. Calculate the speed of the particle after 1.5 seconds. Now, the problem with this graph is we're trying to calculate the speed of the particle at a specific point in time. And that's fine if the graph is straight, but this graph's got a curve, and we need to calculate the gradient. And if we want to calculate the gradient, and the graph is curved, we're going to need to draw what is called a tangent. Now, a tangent is something that touches a line, sort of very slightly, and then goes up. That's a really bad example of a tangent, but I might be able to draw a little bit of a better one. Almost, it should really touch it, and it's a straight line. And what you need to do is you need to make sure that the tangent is the same gradient as the line at that point. So what you'd do is you'd line your ruler up so that it was at the same. It was at the same slope as the graph at 1.5 seconds, and then you'd rule a line, and it'd slightly touch at this. It should touch at this point as well. I can't do it on here, but yeah, it touched at that point. And then, because you've got a straight line, you can calculate the gradient of that line, and that's going to be the gradient at that point in time. So what I've done here is I've drawn a tangent. It's just touching at 1.5, and I've lined it up so it's at the same gradient at that point. So it's at the gradient is the slope. And what I'm going to do is I'm going to need to calculate the change in y over the change in x of that line, because the gradient is the change in y over the change in x. So if I have a look at the scale of this graph, well, it goes up, each 5 boxes is equal to 10 because it goes from 60 to 70. So each box would be, if I'm splitting 10 into 5 boxes, 10 divided by 5 is going to be 2. So each box is equivalent of 2 metres. So I've got 60 and then 3 boxes up, so that's 66 here. But then I'm finding the change in y, or the change in distance, not the overall distance. So it's 66, which is here. And then I measure the point here, which is, that's quite easy. It's just 10 metres. It's halfway between 0 and 2. So it's 66 take away 10. And that's the change in y. the change in x is, okay, I'm reading off this scale here, and I've got 1 to 1.5 is 0.5, so 0.5 is divided into 10 boxes. So if I do 0.5 divided by 10, that's going to be 0.05. So each box is equal to 0.05 seconds. I've got 2 here and I've got 4 boxes across. Well, 4 times 0.05 would be, it'd be 2 plus 0.2, which would be, so this point would be 2.2 seconds. And this point here is halfway between 0.5 and 1. So halfway between 0.5 and 1 is 0.75. So I'm going to do, so I've got 66 minus 10 over 2.2 take away 0.7, because that's the change in distance over the change in time. And we know the change in distance over the change in time is equal to the speed. And that would be 38.6 metres per second. Now, there will be a bit of leeway with questions like this, because when people draw tangents, they're not going to be absolutely perfect. So exam mark schemes will give you a little bit of leeway for errors that come in. But just try and make sure you line your ruler up at the same gradient, and the tangent should just touch the graph very slightly, and you should get something that looks a bit like what I've got here with my black line. And then what you do is you calculate the gradient of that tangent, and that's going to give you the speed at that point. Or you might have to calculate tangents for other things. It's like rates of change. In this case, it's a change in distance over the change in time. But you will have other change of rate questions in the maths syllabus. Right, thank you for watching. Hope you found that helpful. If you liked the video and like to see more, please hit the subscribe button. And for practice questions, please visit www.mitchellmathsandscience.com. The link is in the description.